Okay, so this screencast's about commercial cells, and it's part of the redox unit for year 12. Um, the commercial cells that we need to look at are primary, secondary, and tertiary cells. So the lead acid battery is an example of a secondary cell. It's a cell that can be both discharged and charged. So it's able to produce voltage, and it's also able to be charged again, and the charging process is essentially pushing back the spontaneous reaction that happens when it produces voltage by supplying it with electrical energy. These batteries have been around for a long time, and if you're not sure what a lead acid battery is, it's the type of battery that you would find in a car or boat or some other sort of large piece of machinery. So it's very heavy, owing to the lead, but it is very good at producing quite a large voltage. So here's a schematic of the lead acid battery, and it is producing voltage. So it's in discharge at the moment, and we can see that by the I here denoting the direction of current. You can see we've got two electrodes. We've got the lead oxide electrode, PbO2, and we've got the solid lead electrode. The electrolyte in this case is sulfuric acid, and obviously that has to be with water, so that there's hydronium ions. So if you consult your standard reduction potential table, what you will find is that there are actually two reactions that are taking place. One of the reactions at the anode is where lead is oxidized to lead 2 and produces 2 electrons. And you'll find that just underneath the standard hydrogen reduction. Now it's worth noting that the lead 2 that's produced is then almost instantaneously there's a precipitation reaction, and that forms lead sulfate, and the sulfate is present due to the presence of the sulfuric acid. At the cathode, you can see there's a similar reaction with the lead oxide, but obviously this is because it's at the cathode, it's a reduction. So here we're gaining 2 electrons, and we also form lead sulfate. Now, when you add those together, you can see that essentially at the end what we end up with is lead sulfate and water, and we get an E0 for the cell of plus 1.82. So when the battery is fully discharged, essentially what we have is lead sulfate. Okay, so when we recharge the battery, what we're going to do is we're going to force those two reactions that we've just seen to go in the opposite directions. And what happens then is the lead sulfate is broken down with oxygen from ionized water, and the lead oxide that is subsequently then produced is deposited back onto the positive electrode, and the lead is deposited back on the negative electrode, and so we end up back where we started. So let's have a look. at those equations. So at the cathode, this is what's happening. We get lead sulfate, and when we supply 2 electrons, we form our lead, and you'll see that has an E0 of minus 0.36, and it's probably worth finding these on the table and also asterisking them so that you know that these are relating to the lead acid battery. And then at the anode, you can see this reaction, the lead sulfate with water, is making lead oxide, the sulfate ion, some H plus and 2 electrons, and that's 1.69. It's the third from the top. Negative 1.69, I should say. Okay, so that's the lead acid battery. You also need to know about tertiary cells, or also known as fuel cells. And the idea of a fuel cell is that it is something, it's able to produce voltage and produce electrons through a reaction with 2 reactants that essentially are being constantly replaced. So once they react, they are used up, but because they are being replenished all the time, the voltage continues until those 2 reactants run out. Now, it's mentioned in the syllabus that you need to use a hydrogen fuel cell. So you need to know about a hydrogen fuel cell. So the hydrogen fuel cell requires either an acid electrolyte or an alkaline electrolyte. In any case, either of those reactions, the overall reaction is the same. We have hydrogen mixing with oxygen, and we produce water. Now obviously this is quite an attractive proposition. We can produce energy, and the only product from that is water. However, producing hydrogen is quite an energy intensive process, and obviously there's implications with storage of hydrogen, so it's not the ideal thing that at first it appears to be. So the 2 reactions that concern you in acid conditions is H2, so hydrogen gas, hydrogen gas forming hydrogen ions and 2 electrons. So that's your 0 exactly standard hydrogen electrode half cell potential. And then we've got O2 with 4H plus. Now these have E0 that has an E0 value of plus 1.23 volts. Okay, so that's in acid electrolyte. In alkaline electrolyte, then the reactions are as shown, and you should probably take some time to find those also on the standard reduction potential table. So, in essence, how it works, on this side we've got some hydrogen, on this side we've got some oxygen. There is an anode and a cathode, and they're connected to a wire, and here we've got some load or an external circuit, and there in the middle there is some sort of membrane where the 2 substances react. So on the left hand side what you're going to see is hydrogen fuel coming in. On the right hand side you're going to see oxygen fuel coming in. You're going to see the subsequent reaction and some electrons that are produced. So there's the hydrogen. Once that reaches, sorry, that's my dog. Once the hydrogen enters the fuel cell, it's going to ionize and produce electrons. Electrons are going to whiz around the circuit. The oxygen which is going to come in is going to pick up those electrons and form water. Oh dear. I think something's a bit wrong with that animation. Apologies, I'll fix that up and perhaps we'll show that to you when I'm back at school. Alright, hopefully that makes sense, and I'll look out some questions for you to do on hydrogen fuel cells and the lead acid battery.